Okay, well, hello Bailey, and hope you're feeling better as you watch this. And you can thank your classmates for the interesting discussion we've just had about
The environment.
yeah,
It's good.
non-mathy things. So as a result, this video will not be as long as you feared. Um, so it looks like I have about 48 minutes left. That's okay. In fact, it might even be less than that because all I have left in the chapter, these 2 pages of notes. So as soon as I get through them, we're gone. Uh, so let's see how this goes. But my usual tendency to go off on tangents still applies. So sorry, not sorry. Okay, so to wrap up finite difference methods. About error analysis. This is section 2.4 in the notes. And although it's going to be about finite difference methods, really the concepts that I cover here are useful for studying numerical methods for really ODEs and PDEs in general, even if it's not necessarily finite difference. So to be concrete, we'll focus on the equation we have together, the Poisson's equation in 1D. So U double prime equals F. Now elsewhere in the chapter I've had minus, but I guess I'm just negating F. So that's what we're going with. And we'll assume, even though it's not really a big deal for this discussion, Dirichlet boundary conditions of some kind. So when you discretize this PDE, even though it's technically an ODE, you get a system of equations, as we've seen. I'll write as AU is equal to F. So A is probably that matrix that, well, actually, in this case, it would be that matrix that has like 1 over h squared. And then you have minus 2's down the diagonal, and 1's above and below. So the matrix for the center difference for the second derivative. The vector f would account for the function f, as well as any additional terms due to the boundary conditions. So our computed solution is just going to come from solving this system. Okay. Now, notation. U is, okay. All right. I'll define U hat. The vector U hat consists of the values of the exact solution at whatever grid points we have. So you have n grid points. So h is equal to 1 over n plus 1. We'll just assume that we're working on the interval 0 to 1 for concreteness. All right, so this is u of x equals the exact solution. Whereas this vector u without the hat is going to be our computed solution at the grid points. Okay. Now, our computed solution satisfies this system exactly, except for round-off error. But we're not going to talk about round-off error here because this is not 560. You're welcome. Now, this vector is not going to satisfy this exactly. There's going to be some error left over. So what we can say is that A times U hat, we'd like for it to be equal to F, but it's not. It's equal to F plus some error vector that I'll call tau.
And this is from using that you had?
Yes, this one.
Okay.
Yeah. Now, the vector tau, very important entity in error analysis, important enough to give a name. This is called the local truncation error. Or LT. Okay. Now, local truncation error comes up very often in error analysis of numerical methods for all kinds of differential equations, whether it's Poisson's or time-dependent equations, heat equation, wave equation, any of them. And therefore, for each kind of problem, it's going to have slightly different definitions. But I'm going to give one generic, entirely verbal definition. So to keep in mind whenever you're dealing with anything related to local truncation error. Local truncation error is the residual that comes from substituting this is the important part right here, the exact solution into the numerical method. So that's always the way it works, because the exact solution satisfies the PDE exactly, the exact solution. Will not satisfy the approximate equation exactly. There's going to be something left over, and that's what this tau is. Similarly, the computed solution satisfies the numerical method exactly because it's generated by it. This would not satisfy the ODE or PDE exactly. Again, it's going to be something left over, but we're not thinking about that. We're substituting the exact into the numerical method. Okay. So in this case, tau is equal to AU minus F. AU hat minus F. Okay. This is similar to the notion of residual, like for a system of equations, AX equals B. So when you have AX equals B, that's the same as saying B minus AX is equal to 0. So if you plug something else in for X, that's other than the exact solution, so you get B minus A times X tilde or something, that's not going to be 0, it's going to be something left that's called the residual. So for some reason, these notes, residuals defined at the opposite sign, AU minus F instead of F minus AU. But we'll just go with it. Okay. Now, the reason why we work with the exact solution, even though we don't know it, is that it is still viable for error analysis, because we're not actually computing anything here. We're just trying to figure out, get an idea of how accurate our method is. When you have the exact solution, that's good for Taylor expansion, because you can use the fact that the exact solution satisfies the PDE exactly, and that lets you simplify what you get. So I'm going to show you what I mean by that. Because right now, we have this definition of tau, and we don't really know anything about it. We want to try to get a handle on how big can this get? how does it relate to, for instance, a parameter h, our grid spacing? Because as h goes to 0, presumably the error should go to 0. But does it? We don't know yet. Okay. So a Taylor expansion of one component. Remember, tau is a vector. Everything in here is a vector. So we're just going to Taylor expand one component of tau. So what we have is tau I is equal to the ith component of AU hat minus, the ith component of this vector, but that's just going to be f of xi. To simplify things, we're going to assume that this is an equation in the interior, but we're not dealing with boundary conditions. Because otherwise I might have a boundary term included in this, but we're just going to assume we're in the interior of a domain so we don't have to think about it. Okay, now, what is this? Well, here's where we use the fact that A is this matrix. So that's going to be 1 over h squared, and then this matrix, so minus 2, minus 2, minus 2, diagonal, 1s and 1s, times the vector u of x1, u of x2, u of xn. Now, all this is a vector, but I only want one component of it, component number I, and then minus f of xi. Oh, should be a 1 sitting here. So I want to take row I of this matrix and multiply that with this vector. Now, if I'm taking one row of this matrix, multiplying by this column, that's a dot product. Yes?
Why the matrix and the vector A and U are in parentheses with a subscript of I? What is that?
Because matrix times a vector gives me a vector,
Right.
and I want component I of that vector.
Okay.
So it's this I is this I.
Right. Okay.
Okay.
Yep.
Yeah. And taking one component of a matrix vector product is equivalent to, okay. Slight digression, but this is important linear algebra knowledge. Sorry, Bailey. Okay. So we're taking component, ith component of a vector, any vector, I'll call it V. That's the same as EI transpose V, where EI is this vector. Well, actually, you know what? Actually, only one person in this room took 610 last semester, and therefore should know what EI is. Sorry.
What was 610?
Oh,
I'm just
was this close to flunking? Okay.
EI isn't E the all the ones?
Oh, so sometimes we use E, but with no subscript to refer to a vector of all ones, but this is something else.
Well, it's the transpose, so it's an array of all ones.
Well, it makes it a row vector, but forget the transpose part now. So EI is a column vector, and it is
Am I thinking of something completely different?
you might have been, yeah. But for the purpose of extracting rows or columns of a matrix,
What is E?
E sub I, the subscript is important.
I mean, it looks familiar, but I'm thinking of that E, like E is known as 0, 1, 0, or it's like
Oh.
0, 0, 0, 0, 1.
Yes, that's it. Yes. It's the ith column.
That's what I said the first time. Well, maybe I said it was all ones.
Yes, that's what threw me
That's
off.
Okay, it's 0, 0, 0, 0, 0, and the ith is all
Yes. Okay. All right. So you had the right idea, just weren't expressing it right.
Yeah.
Okay.
I
So
do that all
okay.
I do that all the time.
I know. Okay, you get a gold star anyway. So, yeah, so it's all zeros with a 1 in the ith position. Okay. Therefore, it's also the ith column of what? Yes, it's the ith column of identity matrix. All right, gold star for you too. Okay, so ith column of identity. So this dot product would be in 0, 1s, all zeros, times v1, v2, vn. And as I said a few minutes ago, make sure this is still recording. Come on. All right, I'll just assume that it is.
So that over there is B.
Yeah.
Yes, this is v.
I'm sorry. Well, all of that is
Oh,
also. So how is that also B?
okay. We should have that in language more often, emphasizing that. Okay, yeah. Okay.
We're asking lots of questions.
Yeah. Okay.
I thought you liked questions.
Yeah.
What? I do.
Okay.
What made you think I didn't like a question?
You seem to know. I'm just kidding. That's an N, right?
Yes.
Yeah.
Yes. Well, I definitely can't fault questions for my penmanship. But no, I was not annoyed by Sarah's question. I was trying to think of the easiest way to resolve it. Okay. Anyhow, row vector times column vector is dot product. So since everything is 0 here, most of these are going to be gone except for the ith one. So that's the I. Now, to apply the same idea to over here, where I want the ith component of that. So A times U hat's component I is the same as EI transpose A U hat. But that is the same as row I of A, so that's a row vector, times U hat. Because this is row I. So to extract a row of a matrix, you multiply on the left by EI transpose. To extract the ith column of a matrix, you multiply on the right by EI. Because what I was about to do was take ith row and take a dot product with U, but I didn't really explain where that came from, so here it is. All right, but this is one of those things that it's important at some point it becomes second nature, like, oh, ith column, that times EI, etc. Just because it comes up a lot. Okay, so in this case, that row I would be 1 over h squared times a vector that only has 1, minus 2, 1, and the rest zeros, times this vector that's u of x1, u of x2, u of xn.
So the rest are zeros?
Yes. Yeah. Now, the minus 2 sits in the diagonal. This is row I. Therefore, the minus 2 is in position I, column I, because it's on a diagonal, I entry. Therefore, this 1 is in position I plus 1, and this one is in position I minus 1. So that tells me when I take the dot product, I'm going to get 1 over h squared times uxi minus 1 minus 2 uxi plus uxi minus 1.
Plus 1?
Yes, plus 1. Okay. Now that I've taken too much time on that, and I only have 28 minutes left. Yeesh. Okay. So the LTE at this point is all that. Let me make sure I'm getting a. Yeah, I am. Okay. U of xi minus 1 minus 2 uxi plus uxi plus 1 minus f of xi.
Why is it 1/2?
It's not. 1 right squared. Wow, I'm really off today. Okay, now this right here is the center difference approximation to u double prime. And we know we have an error formula for it. So this is equal to u double prime at xi, and then I have to include the error term. The error formula, which actually, yes, I did derive, I believe, a couple classes ago. 112. Oh, did I? I better make dang sure that I did, but, well, I can't do that now. Okay. Fourth derivative. Actually, let's see. On that day that I covered it, I believe only you and Bailey were here. Can I look at your notes from...
Yeah, I don't remember having 112.
What?
I don't remember that.
Yeah, so I'll see what I did do.
That's-
Oh yeah, it would be finite. Yeah, let's start with finite difference. Okay, I did all that, because I derived the centered. Okay. Oh, yeah, it is there. Okay. Okay, good. All right, so fourth derivative over 12. Now I'm going to write it slightly differently than what is in there, but at xi is really supposed to be an unknown point. But I can say at xi, provided I account for other Taylor series terms that follow, but those would be of order h to the fourth. So the center difference approximation over there becomes this. So it's approximation u double prime, and that is the error in the center difference. Okay, and then I still have a minus f of xi. Okay. Whoops. Sorry, Bailey. Okay. All right. Now, this is where we see the benefit, finally, of doing Taylor expansion. Because before I had like uxi minus 1, u of xi, uxi plus 1. And we need to relate that to a derivative. So we use the fact that that's the center difference formula. And now u double prime is in here. Now, I've yet to actually use the knowledge, the assumption that u is the exact solution. The exact solution of what? What PDE does u satisfy exactly from the very beginning of your notes? No.
Raise.
What?
That's weird.
Linear.
Oh, no. Beginning of today's notes, not the.
Oh, I was
Sorry.
like,
Thinking back too.
Poissons.
Yeah. More specifically,
The one-dimensional.
the actual equation. Yeah, but the actual DE.
U double,
What? No, that's the numerical method.
U double prime equals F.
That one. Yeah. Yeah, that's the original. Yeah. Okay.
I read the right side.
Okay. All right. So u double prime equals F. So I can fill that in. And voila, cancellation. So all that's left is the error term from the center difference. Wait, I missed something. There's supposed to be an h squared in here. Okay, let me fill that in. So 112 fourth derivative times h squared plus terms of order h to the fourth. So that is a local truncation error. I can condense this by saying this is big O h squared. So, in other words, the local error, locally, this numerical method is second order accurate. Okay. So, questions about this simplification of LTE? All right. Now, but that's not really the error we care about most. What we really want is global truncation error. So GTE is defined to be the computed solution minus the exact solution, evaluated at the grid points. So it's also a vector. This is what really matters. And having small local truncation error is nice, but if you still have large global truncation error, then you can't really say your solution is accurate. And this is the actual difference between what you want and what you have. But global truncation error is difficult to analyze directly. That's why we use local truncation error to help us do that. So while this is the end goal, we really need both. Now, the nice thing is, I can relate the two, but I can take this equation and multiply both sides by A. So AE is equal to AU minus AU hat. But AU is equal to F. So this is minus the local truncation error. So that's how the two are related. So in other words, basically, so the exact error substituted numerical scheme is the local error. Okay. Now, so here's how this can help us. All right, at least now I'm on the last page. So E is the same as minus A inverse times tau. So I'm just multiplying both sides by A inverse, just to isolate E. And now I can take norms of both sides. So the magnitude or norm of E, so that's okay. Now I can drop the minus because if you scale a vector by -1, and if you negate a vector, that doesn't change the magnitude. Also, a property of norms is that the norm of a product is less than or equal to, whoops, I forgot the inverse, less than or equal to a product of the norms. Okay. Oh, that? Yeah. Okay. There's something else missing? Or? Okay. Okay. All right. So what the significance of this is, if we get a handle on how big this is, we already know it's order h squared. If we get a handle on how big this is, then we have a bound on the global error. And that's all we really want. We're not going to figure out the error exactly. If we could, then we'd have the exact solution. But if we can come up with an upper bound on the size of our global truncation error, then we know how accurate our method is. Okay. Now, so now suppose we solve this equation, u double prime equals f, and therefore we really solve on a grid with spacing h. All right. Now, this leads to a system of equations. Now, I'm calling this AU equals f, but what I'm going to do is I'm going to put a subscript h for all these entities just to emphasize that we're working on a grid of spacing h. Okay. All right. Now, so what that means is the error on this grid of spacing h is less than or equal to the norm of AH inverse times the norm of our local truncation error, again, on this grid. And we've already seen that this depends on h anyway, because it's order h squared. Okay. Okay. So, here's the remaining issue. How does this behave? As h goes to 0. Now, because you might be thinking, well, this local truncation error, we already know it's order h squared. So you might be thinking, well, if the local error is order h squared, surely the global error is too, right? The problem is we don't know that necessarily. Because what if, as h is going to 0, okay, we know this is going to 0, but what if this is not? What if this is getting larger? Because this is a larger and larger matrix. Like, if you're using spacing h, that means you're using n grid points. This is an n by n matrix. H goes to 0, this matrix is growing. What if its magnitude, what if its norm is growing with it? So there are numerical methods that have this problem, where as h goes to 0, this can grow, so that maybe the error the global error does not go to 0. So now I'm going to define the essential terms of error analysis. And given everything I've just written down, turns out the definitions can be stated very simply. It looks like I'll be done in time. Okay. So these are terms that really need to be burned in your brain because they're going to come up all the time. And if you do your research in methods for ODEs or PDEs, they got to be off the top of your head. I'll quiz you on. I'm half joking. Okay. Okay. The first is consistency. All right. So we say the scheme is often used to refer to a numerical method. Why, I'm not sure. Sounds kind of nefarious, but there you go. So the scheme that's described by this system of equations, A, H, U, H equals FH, which depends on the spacing H, should be the H there, okay, is consistent if the limit as H goes to 0 of the local truncation error is 0. Now for this scheme, we already know that's true because we saw that the local truncation error is order h squared. Second concept, stability. This is one that wrecks convergence for a lot of schemes. So the scheme, same scheme, is stable if the norm of AH inverse is bounded by some constant C for H sufficiently small. Okay. And what's very important, the constant C has to be independent of H. So some fixed constant that bounds the magnitude of AH inverse. Okay. Another way of saying this is the norm of the inverse is uniformly bounded. So there's one bound C that applies.
The scheme is.
Well, no, this norm is uniformly bounded. Yeah. And it doesn't have to apply for all H, just H that are sufficiently close to 0. Okay. And finally, convergence. So we say the scheme is convergence if the global error goes to 0 as H goes to 0.
E.
Oh, wait, oh, sorry, but yeah. the notes are using superscripts for H. I mean subscripts, but
Is it still inverse E? Or is that the vector line?
oh, that's a vector line. But yes, if it's a global error.
Yeah,
Okay, Sarah.
Yes.
Okay.
Yeah.
All right. Yeah. So if local error goes to 0, that's consistent. That's nice, but not what we really want. If the global error goes to 0, it's convergent. That's what we do want. Okay. All right. Now, dang, 8 minutes. Now there's a nice theorem that relates all these.
Fundamental theorem of error analysis.
that was a really
Well, actually,
That's what I would.
it's not officially called that, but I can believe it. At least error analysis, at least for differential equations, anyway. So it's called the Lax equivalence theorem.
it's ridiculous.
What?
Who comes up with these names?
In this case, it's Peter Lax.
Oh, okay.
Peter Lax. Actually,
I capitalized on it.
it's going to be kind of blasphemous on my part, but I'm going to check and see if he's still alive. Yes, he is.
Oh, good for him.
He's 93 years old. So. What? All right. He, I imagine retired by now, but a professor at the Cron Institute, NYU. And I have, well, I don't know if I actually met him. I saw him when he was visiting Stanford. I don't know. I don't think I ever actually had a conversation with him. And I'll tell you 2 things about him real quick. This was 15-something years ago. But when we'd be sitting in a seminar, he'd be sitting right there in the front row. And he would be so asleep. His head would be tilted back like that, yeah. But, he's Peter Lax, so definitely allowed. And the other thing I thought was really unusual, when he was the one giving the talk. So he had the talk on transparency, the old-fashioned overhead projector. And so I figured that if you need to point at something and you have overhead projected onto a screen, that you're going to do one or 2 things. That you're either going to point directly on the transparency, or either point directly on the screen, or have a big long pointer that'll point directly on the screen. He did neither. He would point out into the air at the right point, at what he wanted to point at, so his finger would show up on the screen at the correct thing. Yeah, it was like a really freaky superpower. Like that.
It's like his shadow.
Yeah. He would make his shadow point at the right place. Yeah.
That's really cool.
Yeah. So he's the only one I've ever seen do that. So.
A weird shadow puppet.
Yeah. So go figure. So. I hope he doesn't see this. Okay. All right. But this is a wonderful theorem. Well, he has a lot of things named after him. There's numerical schemes named after him, like.
The last scene.
Ours is someone else, like the Lax Friedrich scheme or the Lax Wendorf scheme, things like that. All right. So there's a finite difference scheme. AHUH is equal to FH, is convergent if and only if it is consistent and stable. Okay. So consistency by itself is not enough to guarantee convergence, but if it's consistent and stable, it is. So I can show 1/2 of this very easily, because the norm of EH, which we already saw is bounded by the norm of A inverse times the norm of local truncation error, but if the scheme is stable, I can say this is bounded by some constant C times the norm of local truncation error. So now if you say it's consistent, therefore this goes to 0, that must go to 0 also. So Bam. That's a proof of 1/2. That if it is consistent and stable, it is convergent. I'm not going to do the other half because we only have half a semester. Okay. Now, I've already shown you that this scheme for Poisson's equation is consistent. There's still a matter of seeing that it is stable. And I have 3 minutes to do that. So a nice result from linear algebra, if I work with a particular norm of AH inverse, the 2 norm, so that comes from the Euclidean length norm for vectors. That is equal to, because A is symmetric, that's the key thing I'm using here, otherwise I could not do this, is equal to the maximum of the eigenvalues of AH inverse in absolute value. But the eigenvalues of the inverse are 1 over the eigenvalues of the original. And since I want a max, that's the same as saying 1 over the min eigenvalue of AH. So if I get a handle on what is the smallest eigenvalue of AH, then 1 over that would be the norm. And it turns out the eigenvalues of this matrix for the center difference are known. So each eigenvalue of AH there's a formula for it. And I wish I had time to show you this, but that would take a long time. Cosine, I'll use a J here. Cosine J pi H minus 1. Okay. Now, so if I were to use Taylor expansion on cosine, because cosine, that's equal to 1 minus j pi h all squared over 2. So this one plus additional terms, like something that's order h to the 4th. So these 1's cancel. So now I have this. The 2's cancel. The h squareds cancel. So all I have left is minus j pi all squared plus something that's order h squared. So what this means is, by filling this in here, because I want this to be as small as possible. Okay. Well, I should mention j is a positive integer. So that j goes from 1 to n. So, what's the smallest eigenvalue in absolute value? You said j equal 1. So in other words, this is roughly 1 over pi squared. And as h goes to 0, this part goes to 0 also. So that's a good approximation. So in other words, I can say that for h sufficiently small, that this norm is bounded. So I'm not going to see growth as h goes to 0. That's the important thing. So that ensures that scheme is stable. And from the earlier result as consistent, we conclude that it's convergent. By the way, the formula I just pulled out of the blue for eigenvalues comes from the fact that A is a Toeplitz matrix. So there are formulas for eigenvalues of Toeplitz matrices that I relied on here, so that you can Wikipedia that. So Toeplitz, circulant, those kind of matrices, eigenvalues are known. So it's all great for constant coefficient problems. Variable coefficient problems, we can't take advantage of any of this, but yeah. And that's why I work on variable coefficient problems, because I don't like that situation. Yeah. I've sucked 3 of you into it. So, okay. Well, yeah, sorry, I'm past time, so sorry if I make you late to practice, Jessica. But that's it. The next chapter will be Spectral Methods. Yay, my favorite. I guess I'm forcing it to be your favorite too. But then I'll also plow ahead through homework 1, and we'll talk about some MATLAB stuff next week.
I'm gonna be out.
Oh, right. Both days or just Monday?
Hopefully just one day.
Okay.